This is the physical part of the synthesizer. The way this is going to work is you push a key on the keyboard and the MIDI is going to enter in here from this side. So you begin here, the MIDI signals come in. This part controls both of these control the sequencer action. In order to visualize what's going on and get that visual feedback for what point in the sequencer you're dealing with and all that, then you look at these lights right here. These lights will light up based on what note you're at, or if you want to go back and edit. But to see the sequencer, we have to look at all these lights for feedback. And I'm going to talk about some hardware, namely shift registers, which is what I'll be using to light up these LEDs. And we're going to talk about how to program them and use them. So that's sort of where I'm starting today. What are shift registers? Well, that's a shift register. This thing is a little tiny IC, and what you do is, by register it means like a little place in memory, and by shift it means you can, in a serial fashion, shift in information to be stored in the registers. In addition to that, you can output register values. And by register values, I mean if it's an 8-bit register, which is what this one is, then each bit in those 8 bits will go to a corresponding pin, and they'll be high or low based on whether that position in the register has a 0 or a 1 stored, or a high voltage or low voltage stored. This is the data sheet for the shift register I'm using. I'm just going to give you the quick and dirty what happens inside of this thing. This OE is an output enable. Whatever's coming out of the shift register will be allowed to pass to the outputs themselves. If you set RCLK, then it'll allow whatever's in the register to go out through the output enable, or to the output enable. And then whether output enables on or off will allow it all the way through. Then there's this SRCLK here. This SRCLK is the serial clock. As you pulse serial clock, then you can make serial high or low, depending on what you want. And whatever it is, if it's low, then each clock pulse will make this first register high or low. And then if you pulse the SRCLK clock again, then if this is high or low, as that gets pulsed, then the next register will take on that previous value. Anyways, let's get started. We're only doing pin toggling, so we don't need the driver lib library with us. This is all we need. And I'm also going to make this code a little general. So I'm going to do it like this. So once again, these define statements, if you're not familiar with C, these are string replacements, which happen before the C compiler takes over. So we're going to say the MSP, which has multiple ports. We're going to use port 5, the latter half of it, in order to work with the shift register. This is port 5, pin 4, pin 5, pin 6, and pin 7. So we're going to make the serial clock 5.4, serial input 5.5, and so forth. And so with that, we also need to enable the GPIO pins for those corresponding things. So let's go ahead and throw that in here as well. All right, so that's taken care of. The other thing we need to do is time this thing. We can't just toggle away and send information in as fast as we want to. I mean, we could, but what we want to do is time it. So I'm also going to set up a timer. So we have our pins set up, and we have them named so that we can use them. What this allows you to do, these define statements, is if you just move to another microcontroller, you don't have to rewrite all the code, you just change what pins you're connected to. We want to set up our timer and all that stuff. Or not our timer, but the code that's actually going to be running. So if the timer went off and it changed timer flag to 1, and reset it, and then we can go ahead and do our shifting. In this scenario, what I'm going to do is I'm going to sweep the inputs. So for the shift register pins, we have outputs 1 through 8. And what I want to do is I want to set input 1 high and the rest 0. And then I want to make only input 2 high, then only input 3 high, then only input 4 high, and so forth. And that way, if you look at a row of LEDs, you'll just have a light bouncing back and forth. It takes time to shift, basically. So every time you pulse that clock, you throw 1 bit in there. So if the shift register holds 8 bits, at minimum, you need to shift 8 bits in, which means you need to toggle the serial clock up and down 16 times. So that way you get 8 clock signals. And so what we need to do is we need to shift information in, and then when we're done shifting all the information in on multiple clock signals, then we're going to output it. So if we've shifted everything in and we're done, then we're going to move that bit around. All right, so and I'm going to do this as well. Move, I'm making a direction. So if move is 1, then we're going to move the light one way. If move is -1, then we're going to move it the other way. That's all. All right, and this is data just has 1 bit that's high, and we just shift it over to the left by 1 bit. And this is, we're going to keep shifting the bit up higher and higher. If we've shifted the bit all the way up to the end, then what happens is we're going to change the direction that we're shifting the bits. So that's all. When we hit the top, we're going to move it back down, and as we go down, then we're going to move it back up. And then we'll do the opposite here after. After we've done that, we're going to write all this to the shift register. So whatever the new data value is, which is just a bit moving back and forth, we will serially write it out to the shift register on a clock pulse. All right. Here, let's initialize some stuff. So we're going to set the initial data to just have a 1 someplace and initialize the move direction. Okay, so the next thing is outputting on the shift register through this write shift register LVV. So this LVV has, I think, 3 shift registers in it. I'm not going to write all this code. It's going to be fairly quick, this one, because I actually have everything very explicit. So let's look through this. So we have the data that we want to shift in. So shift count is whichever shift clock cycle we're on. So if we're on 0, we begin 1 clock cycle, and if we're on shift 1, we end a clock cycle, and so forth. So that's a high pulse, low pulse, high pulse, low pulse, and so forth. And then every time we run through our while loop and the timer gets triggered, then we're going to increment the shift counter and go into the next case. So the first thing that we do is we have our shift port. So this shift port is labeled here as P5 out. P5 out is a variable that goes to the shift register, to the register itself in the MSP. So if I said P5 out equals something, then whatever equals will be written to the output pins. Then we have SR clock, that's on bit 4. So if we said P5 out equals SR clock, then the 4th bit on P5 out on the port 5 register of the MSB will be high and everything else will be low. Then we have same for serial, then the register clock and the register clear. All right, so what we first do is we set all those pins to 0 right here. And then the next time the clock gets triggered, what we do is we end up taking the register clock and making it high. And then on the next clock cycle, we make it low. So we set everything as 0 going into the shift register, and then we high-low pulse the register clock. And the serial clear, because we set that low beforehand and pulsed the register clock, what we do is we ended up clearing everything out of the register. Okay, so then we bring our register clock, after we pulse the clock, we bring the serial clear port high again. What that does is it allows us to pulse the register clock without clearing the register itself. So as we shift information into it, it gets kept in the registers. So then we're going to bring the register clock back low again. And then this is how you actually write information into a shift register. So what we do is we take whatever our serial output is, or this is how I'm doing it, and we set that low. So whatever out of all the pins connected to the shift port, the one connected to the serial data input to the shift register gets set low. And we don't change a clock pulse here, so we can still affect it without changing in the information inside of the shift register. And then our data is our input. In this case, we do a right shift of 0, so it doesn't move anywhere. And then we bit and it with just a 1. So whatever is in the first bit still persists here. And then we left shift it over by 5. So if we have a 1 and the least significant bit, then the pin that goes to the shift register's serial input will be high. And if our data is low in the least significant bit, then it'll stay low. Then we pulse high and low the serial clock, and then we're ready to write the next bit. So now we make the second bit the least significant bit, do the same thing, and then write that. And then we shift it again. And then so we do the third bit, fourth bit, and so forth. This whole time we're not pulsing the register bit, the register clock on it at all until we finish shifting everything in. Then we pulse the clock itself. So register clock goes low, then high again, and then that commits whatever information that we shifted into the register, commits it to the register itself and gets outputted. And then we increment our shift counter. That way on the next clock cycle we start the next series of pulses that we need to shift the new information coming in if we've changed it. And at the beginning, the first 5 tasks we did, or first 5 clock cycles, what we ended up doing is we cleared the shift register. So after we've already gone through this once, we just skipped clearing it again and continue shifting information in. At this point, I think we can put the shift register stuff together. All right, so I got our breadboard here, our shift register. We'll go ahead and set this here. This pin is set up 2 volts to 6 volts here, ground. This is where your serial data input is, the output enable, register clock, serial clock, then the serial clear. And then we're going to use the 4 most significant bits to see what's going on here. I've got 4 LEDs. All right, so LEDs and also their resistors. And I'll just plug this up and we'll see some photons, man. All right, commit the code and see what happens. I'm only showing 4 of them, but out of like 24 bits, so 3 registers worth, I have a light that's going from the least significant bit that's being shifted in to the most significant bit, and it's just incrementing by 1 back and forth, just like that. And so this will be very useful when we use the sequencer, and as it pulses, as the sequencer increments through itself, we'll be able to tell what note we're on, and while we're writing what notes to play into the sequencer of the synthesizer, then we'll be able to know which stage we're on if we want to go back and edit it, if we're currently editing that one, and if there are any pauses instead of notes already written on the sequencer. So there we go, bare bones. Let's hook it up to the synthesizer itself. All right, this is the mess of a synthesizer. Let's see if I can give you a view of the shift registers. All right, there we go. 3 shift registers. They already have the resistors for each output on them set up. Let's see if I can get a better focus. And each of these outputs only go to LEDs. They don't go to anything else. So I have 3 of them tied together. The output of one shift register is connected to the serial input of the one next to it. So in this case, we get 24 discrete outputs that we can control individually, and with only 2 pins. Isn't that awesome? All right, so you can see a couple things that appear. One is the row of 16 inputs for the sequencer, and this is a digital synthesizer, so I could actually make it almost as long as I want, but I only have 16 buttons, and I'm not going to put any more buttons. I might be able to use some toggle flips to go to the next set or whatever, but we'll do that later. There's a red light over here. This red light will indicate rests, and then there's 2 up here and 2 right here lights. These are the modifiers. Their oscillators are not controlled from the keyboard. They're user defined. So just as feedback, these will blink at the pulse of the modifiers themselves. And these 2 up here, the first one on the side over here, if you remember me saying this is going to be the sequencer, so this is going to adjust the speed of the sequencer while it's running, and this light will give feedback as to how fast it's running. This next one is a portamento, so if there's a glide that appears as you push notes, it'll light up for feedback so you know what it's doing. But yeah, that's shift registers. You can use them for a number of different things. One is if you have a low frequency digital to analog converter that you're using. I mean, like it's maybe 1 kilohertz or I don't know, 20 kilohertz or something, then you could get away with using shift registers to access the inputs to a digital to analog converter if it doesn't already have some sort of shift register in it. Another thing that you can use it for, which I am using it here, is I have about 50 something digital inputs. Those will also all be controlled by another set of shift registers, where there will be 2 shift registers just blinking their output like this, signaling one at a time, and it'll go to a whole bunch of the digital inputs here, and the whole line of digital inputs that'll be hot at that point will go to their own inputs to the microcontroller. So you get this matrix sort of where you have inputs going into things and then outputs going into the microcontroller. All right, so we have here 2 shift registers. This is the second one that I made, so it's a lot cleaner. But these two give you 16 outputs, and we're just going to incrementally, one at a time, make them hot. It's going to light up some of these inputs here. Then it gets passed through this bank of diodes, and that way if you press a couple buttons on different parts of the matrix, you don't get a ghosting effect, which is when if you push button 1 and button 8, button 5 may appear to be pushed, but it's actually not really pushed. It's just a effect where voltage is being rerouted through wires. So you put these diodes so they only go one way. And then, let's see, sorry. Woo, fun. And then you have, the inputs to this diode matrix is coming from each of the inputs here. And then eventually they're terminating from these wires, which will go to 5 distinct inputs to the microcontroller. To give you an idea of how fast this will run, I'm pulsing 16 pins at a time. Each time I pulse one of these, there will be a bunch of these lit up. Actually there will be 6 different inputs that will be lit up at a time. Then we'll read it from there. And we'll be able to scan every input, digital and analog, before we repeat this process at 30 hertz. So, around 30 hertz. So, yeah.